Today we're going to talk about pulse repetition frequency because a lot of people are frequently getting a lot of questions about PRF on their SPI boards. First off, you're going to have to know that PRF has no relation to operating frequency. They are completely separate. PRF is defined as the number of pulses that occur in 1 second. It's determined by the number of foci, scan lines, frame rate, as well as the depth, and of course the sound source. Half of the pulse repetition frequency is the highest frequency shift that can be measured. This is called the Nyquist limit. If you look at this color map here, this represents not only the PRF, but the scale, Nyquist limit, and the wall filter. The purpose of this video is to go through all the advantages and disadvantages of PRF. You might not be asked what are the advantages of PRF or the disadvantages, but you might be asked what will happen when you increase your PRF or what will happen when you decrease your PRF. Let's start with the advantages of increasing PRF. And what this will do is improve lateral resolution. And how it does this is when we go back to one of the things that determines PRF, which is the number of foci, when you increase PRF, you're not increasing the number of pulses per frame, you're increasing the number of pulses per second, which will increase the number of foci, thus making it a multi-focus and improving lateral resolution. It improves temporal resolution as well as frame rate, because when you increase your PRF, you're imaging in a shallower region. This will decrease your imaging depth. But keep in mind, you're not actually decreasing the depth. The PRF depth is decreasing. It helps eliminate spectral Doppler aliasing for pulse wave Doppler, and it increases scale, Nyquist limit, and the wall filter at the same time. When you look at this image here, you can see that there is normal laminar flow. Laminar flow is detected more closely to the baseline here. So blue and red are laminar flow, as opposed to lighter blue, orange, and yellow. These colors represent turbulent or chaotic flow. You can see in this image, the colors are more laminar, representing a darker blue and a darker red. When your PRF is adjusted optimally, you will not have any aliasing. When we look at the spectral Doppler here, you can see that the PRF is increased and optimized because we can see the entire waveform without any overlapping or aliasing. These are the advantages of increasing PRF. Now let's talk about the disadvantages of increasing PRF. The first thing is that it will cause range ambiguity, also known as depth ambiguity. This occurs when an echo is incorrectly displaced closer to the surface. And it's the inability to determine the depth of the reflector if the pulses are sent out too fast for them to be timed. It decreases penetration, and it removes color Doppler from vessels. When we look at this image here, you can see the direct effects of increasing the PRF too high because there are areas that are void of color. When we look at this image here, the arrowheads are pointing to the range ambiguity or depth ambiguity artifact that's being placed more superficially from the deeper regions. To resolve this artifact, you're going to have to decrease your PRF, which will increase your PRP, which will get rid of this artifact. Then to fix this image, you're going to have to decrease your PRF, and if that doesn't work, you can also increase your color gain. The advantages of decreasing PRF include it helps fill in color Doppler in vessels, especially the deeper vessels, and it provides deeper penetration and increases imaging depth. In this image here, you can appreciate that the vessels are completely filled with color as opposed to this vessel. This is because the PRF was decreased. The disadvantages of decreasing PRF include it causes spectral Doppler aliasing, especially with pulse wave Doppler, and it causes color Doppler aliasing mimicking a disease or a stenotic vessel. In this image here, you can see that the PRF was turned on way too low, causing aliasing artifacts all throughout this color Doppler. Now the reason why there's color Doppler aliasing in this vessel is because the velocity of the blood going through this artery is faster than the PRF provided in this color scale. If you increase your PRF, this will increase the velocity so that you're able to pick up the highest velocity in this vessel. This image here shows spectral Doppler aliasing with pulse wave Doppler, where the waveform is wrapping around on itself, almost touching the other side of the baseline. All the sonographer has to do is increase the PRF to make this image here look like this image here. Then as far as this image here, once the PRF is increased, it's going to look more like this image here. Here's another example of color Doppler aliasing, and the problem with this artifact is it can mimic disease or a stenotic vessel, because you're going to see the same type of artifacts in a true stenotic vessel. When this happens and you know the vessel is not diseased, just increase your PRF and it's going to look more like this one here. Now, if your PRF is too high while using color flow Doppler, the vessels in the body will become void of color, which we talked about. In this diagram here, this line represents a vessel that's void of color, meaning the PRF is way too high, which is making the vessel void of color. This line represents a vessel that's filled with color, meaning the PRF is turned down so that the vessel will fill with color. PRF is high here, which is making the vessel void of color. The PRF is low here, but not too low that it's causing aliasing. In this diagram here, this line represents a vessel that's void of color, and this line represents a vessel that's filled with color. Now you tell me, which vessel or line has a high PRF and which one has a low PRF? This one has a low PRF because the line is filled with color. This has a high PRF because the vessel is void of color. Here's all the reasons why vessels are void of color. The first is your PRF is too high, scale is too high, wall filter is too high, ensemble length is too high. This decreases your temporal resolution in color Doppler, by the way. Frequency is too high, Nyquist limit is too high, and also your color gain is turned down too low. Now let me introduce you to some questions they could ask you on your SPI. Let's start with this one. If you see a question like this that says, what is the PRF if each image requires 60 pulses, but your system only displays 30 pulses per image? Is it A, 1800 kilohertz, B, 1.8 kilohertz, C, 900 hertz, or is it D, 9 kilohertz? If you want more time to try to figure this question out without me explaining it to you, go ahead and pause the video. Otherwise, I'll go ahead and explain this question now. What you're going to do is you're going to take the required PRF to create each image, which is 60 pulses per second, and you're going to times it by the limited amount of pulses that your system can display per image. You're going to take 60 and times it by 30, which will give you 1800 hertz, or 1.8 kilohertz. With this question, don't be quick to answer an A just because you see 1800. Make sure you compare the units with each other, because when we times these together, we're getting 1800 hertz, not kilohertz. So stop for a second and make sure you look at the units, and if you have to convert, then convert. But don't rush through this question and answer too quickly just because you have the right number, because 1800 kilohertz is very different than 1800 hertz. And in this case, you're going to have to convert from hertz to kilohertz, which will give you 1.8 kilohertz. Make sure you know how to convert from hertz to kilohertz. If you have a number that's in hertz and you want to convert it to kilohertz, just move the decimal point 3 times to the left. If you want to convert kilohertz to hertz, just move the decimal point 3 times to the right. Now let's go over a question like this. What is the maximum Doppler shift frequency if the operating system is working at a PRF of 8,000 pulses per second? Is it A, 8,000 hertz, B, 16,000 hertz, C, 4,000 hertz, or is it D, 6,000 hertz? And just like before, if you need more time and you want to figure this out on your own, just go ahead and pause the video. Otherwise, I'm going to go ahead and tell you how to figure this out right now. And this is pretty simple. Anytime you're giving a PRF and you need to figure out the maximum Doppler shift frequency, all you have to do is divide the given PRF, which is 8,000 in this question, by 2, which will give you 4,000 hertz. Let's say they don't have the option of 4,000 hertz as an option on your question. Try converting your option to kilohertz and see if your answer is there. Move the decimal point 3 times to the left, which will give you 4 kilohertz. If you see the option of 4, that's your answer. Let's try one more question, and let's say that they ask you, what is the Nyquist limit if a pulse wave Doppler instrument has a pulse repetition frequency of 20 kilohertz? Is it A, 40 kilohertz, B, 10,000 hertz, C, 20,000 hertz, or is it D, 10 hertz? Go ahead and pause the video if you want to try to figure this out on your own. Now I know what you're thinking, just divide this by 2 and you're going to get your answer, right? When we look at our options here, we have a 10 there, and well, 10 is half of 20, but look, this is saying 20 kilohertz. This is 10 hertz. Don't be fooled. Make sure you check the units before you answer. That means we're going to have to convert 20 kilohertz to hertz, which is 20,000 hertz. Now that we know the converted number of 20 kilohertz is 20,000 hertz, half of 20,000 hertz is 10,000 hertz. Do we have that option here? We do. That's the answer. The take-home message is just be very vigilant and don't be quick to answer your question just because you see a number that matches up. Make sure you compare the units and don't rush through your question. Just take your time and you're going to get the correct answer, because those are easy questions you can get on your test. And finally, what is the PRF of this image here? Well, the answer would be 3 because there's 3 pulses per unit of time. Thanks for watching.